Hi, my name is Mario Vano. I operate an amateur radio station, AE0GL, near Minneapolis, and like to experiment with low-powered QRP hardware. In an earlier video, I provided a very simple introduction to the use of the Siglent1204Xe oscilloscope for RF spectrum analysis. In that video, I showed how to set it up to display a scan of local FM radio stations. In this video, I'm going to set the math functions up to display the in-band intermodulation products from a typical HF two-tone SSB test. I'll be operating the oscilloscope and capturing its screen via the web remote control interface to provide a nicer image. First, I'm going to reset the oscilloscope by pressing the default button. Once everything has been reset in the oscilloscope, we need to set our input to accommodate the attenuator that we are using to connect the signal from our transmitter to the input. We're using a 40 decibel attenuator. So if I select channel 1, probe type, I'm going to select a 100 times attenuation, which corresponds to 40 decibels. Now I'm going to key up the transmitter and use the auto setup button to have the oscilloscope set up some defaults for us, which are in the ballpark of what we want for gain and time base. I'm also going to turn on the measurement function so that we can see what we're doing and do calculations if we wish. The transmitter should be putting out about 5 watts, and we could do the calculations from the peak-to-peak reading that is displayed by the oscilloscope. If we now turn on the math function, we can select the FFT operator and begin to configure it. We're going to set the vertical settings first. We're going to switch to using dBm for our measurements because that's typically what this kind of measurement uses. We're going to set a reference level of 40 dBm because our transmitter puts out 5 watts and 40 dBm is 10 watts. So that will be the top of our display. We're going to set 10 dB per division to give us a nice dynamic range. Now we're going to set the horizontal settings. We want our signal to be in more or less the center of the display, or at least we want the carrier to be there. So we're going to set exactly 14.2 megahertz, which happens to be the frequency I set in for the carrier. And then we're going to try to set a narrower range for the display. When we do this, we discover that the oscilloscope is not happy. It doesn't have enough samples to work with. So we have to, as we increase that setting to give us better resolution, or I should say decrease it, we'll have to slow down the time base And when we do that, it interacts with the hertz per division setting. We have to carefully get a compromise between sweep rate and resolution. And as you see, we've done that. With a sweep rate of about 2 milliseconds per division. We're now displaying the single tone carrier output of our transmitter. If we want to measure a two-tone measurement, we need to make some changes to what we're transmitting. Our levels for a two-tone measurement are typically 1/2 the peak amplitude levels, because that's the way the measurement is specified in the American Radio Relay League method of measuring. We need to generate two tones, not just one, and they can't be harmonically related. So we're going to set a 700 hertz tone and then add a 1900 hertz tone at the same level. To make our measurements a little bit easier, we're going to add another measure tab by pressing the measure button, selecting math as the source and maximum as the type. This will allow us to always display in white at the bottom of the screen the current peak level displayed by the math function. Having done this, we have now got the oscilloscope set up completely as needed for an IMD measurement. An intermodulation distortion measurement shows the spurious products generated when we put two signals within the normal transmitted passband into a transmitter. And they are being displayed here, and we can now measure them using the graticule and other tools that the oscilloscope provides. If you use the cursors and select the cursor function source as math and the cursor to display as Y, we can set the Y1 cursor to our reference level, which was 37 dBm, about 5 watts. If we do this, we can read out levels directly with the Y2 cursor, which will also display the delta Y. So we can see that our two strongest intermodulation products are about minus 31 and minus 32 decibels down below the peak output, which is displayed as 31 dBm. If you're lucky enough to own a 4-channel oscilloscope, the Siglent1204Xe provides a convenient way to display more information in a table. This is found in the Tools menu in the math function. If we turn the peaks on in that menu and show a table and have it show sort by frequency, it will display a summary of the peaks that it finds. Another useful thing we can do in the math menu is go to the Config tab, select Display, and we can now display either the split screen that we've been using so far, an exclusive display that zooms to full screen just the math functions, or a full screen display that superimposes the normal time-based measurement with the frequency-based measurement from the math functions. I hope this video has been useful for you and will help you to use the oscilloscope to improve the quality of the signals generated by your own QRP experiments. With proper attenuators and sampling points, this method can be used with even high-powered transmitters. But always be careful not to burn out your oscilloscope. Thank you for watching.